Yeah, so welcome back. Suresh Nayak from ISI Bangalore will talk about graded modules and coherent sheaves.
Okay, so I can start then. Okay, so hello everyone. So this is basically the topic of my series of talks, duality in algebraic geometry. So my style will be slightly different. What I decided to try out this time is that I'll write everything in advance and I will simply scroll over it and talk about it as it goes on. Uh, the topic of my first lecture was supposed to be coherent sheaves and graded modules over projective varieties. So I will be sort of getting to that, but I thought before that I will talk about some basics of algebraic geometry, since I'm not sure if everybody in the audience has all the background. So unfortunately, still it's going to be the case that if you have seen it before, then it's all you'll find it okay, and if you have not seen it before, then you'll have to struggle quite a bit. So let's see. I'll try my best. So here's a quick summary of. Pretty much this lecture is a summary of algebraic varieties in some sense, basic definitions. Okay, so here's how we start. So I'll start with affine algebraic sets. So let K be a field, but pretty much initially when we do the theory, we assume K is algebraically closed. But otherwise, in fact, we will work with arbitrary fields in general. So affine space is A and K, which is equal to Kn, and an affine algebraic set. These are our basic objects. So basically, duality in algebraic geometry means duality theory for cohomology over the basic objects of algebraic geometry, and basic objects of algebraic geometry are things defined algebraically. Locally, they are coming as follows. So an affine algebraic set in affine space is a zero locus. So Z is my symbol for the zero locus of a bunch of polynomials. So these are polynomials here. I say that somewhere. Okay, so I forgot to say that. But F alpha are polynomials in this polynomial ring Kx1 to Xn. And it's the common zero locus of a bunch of polynomials, and which is the same as the common zero locus of the ideal generated by them. And so, for example, here's a zero locus of x squared plus y squared minus z squared minus 1 equal to 0 in 3 space. Here, of course, I draw it over real numbers because I don't know how to draw it over complex numbers, obviously. So while drawing pictures, we might occasionally draw it over non-algebraically closed fields. But initially, the theory we set up is over algebraically closed fields. And later on, of course, we generalize and we work over arbitrary fields, and in fact, much more general. Okay, so if I is generated by a single element, we'll call it a hypersurface in affine space. And given an affine algebraic set V inside A and K, we'll define, so I of V, this is I of V, and that's the ideal of functions vanishing on V. So that is F in the polynomial ring, such that F of P is 0 for all P in V. And we define the coordinate ring of V to be this collection. So what is this? This is basically the set of all polynomial functions. So polynomial functions on the NK are just polynomials in n variables, but you restrict them to V. So when you restrict them to V, functions which are 0 on V, they should be killed. So that's why I'm quotienting out. So I'm quotienting out by the ideal consisting of all functions which vanish on V. So therefore, when I restrict polynomial functions to V, I don't really get polynomial functions. I get the quotient polynomial ring modulo the ideal generated by modulo the ideal of functions vanishing on V. So for a typical affine geometric object, I associate such a ring, and that is called the coordinate ring of V, and that is that's a finitely generated K algebra. So the useful thing to know about such rings is that you can pretty much recover the entire algebraic set V from its coordinate ring. So for example, so here are some facts which will explain this. One thing is that the maximal ideals in a KV will correspond to points in V. This is known as Hilbert's null Strelensatz. So one can prove this. So this is all these facts can be found in any basic text on commutative algebra, algebraic geometry. So you can look those up. Maybe I think references have been provided. So you can, yeah, I mean, you can find them in most of these textbooks. So this is one example. And then the other one is, for example, you can talk about maps between affine algebraic sets. So take one affine algebraic set V inside A and K, and W is another affine algebraic set. And you look at a polynomial map between them, which simply means that it's a restriction of a polynomial map between AN to AM. So any map from AN to AM has to be given by M functions of N variables. So you simply write down M functions in N variables. This gives you a function from V to W. And so if this function from V to W is a restriction of such a polynomially given map, we say it's a polynomial map. And any such polynomial map induces a k-algebra homomorphism. Basically, any function from V to W will give you a function from functions on V to functions on W, simply by composition. So a function on W composed with phi will give you a function on V. And in fact, it's you see that it's a k-algebra homomorphism. So this gives you a homomorphism of k-algebras. And what in fact one has is a one-to-one correspondence between these two sets. On one side, you have polynomial maps between V to W. And the other side, you have k-algebra homomorphisms from kW to kV. So what this is doing is, suppose I give you a polynomial map phi, then exactly how what we did here, phi star, that is the map obtained by composition. So that gives you a k-algebra homomorphism from kW to kV. And in the reverse direction, if I give you a homomorphism from kW to kV, then basically that because V and V was has a coordinate ring which is a quotient of the polynomial ring in x1 to xn, because it's a closed set here. Sorry, I mean it's an affine algebraic set here, and W was an affine algebraic set here. So its functions are again quotients of k y1 to ym. So any such homomorphism from kW to kV gives rise to, I mean, lifts, because polynomial rings, you have freedom of choice over variables. So it lifts to a homomorphism from ky1 to yn to kx1 to xn. And this allows you to define a polynomial, because this lift will, for each yi, you see what polynomial in x1 to xm you get. And that is your ith coordinate of this map here. So any such lift gives rise to a polynomial map here. And this is actually a one-to-one correspondence, which also preserves isomorphisms. Definition of isomorphisms on the right-hand side is isomorphism of rings, and the left-hand side is a two-way bijective polynomial map. And so isomorphisms are preserved. And so what the net final story for affine algebraic sets is that affine algebraic sets and maps between them are completely determined by coordinate rings and k-algebra homomorphisms between them. So I mean, in effect, you can reduce all questions in principle to questions in ring theory. Okay, so that is affine algebraic sets, but now we need to move on. And so before we move on, we need to set up a little bit of topology on it. So the Zariski topology on affine space A and K is defined as follows. You declare the closed sets to be precisely all the algebraic sets in A and K. So one checks that this actually forms a topology on A and K. So you have to check that it's preserved under finite unions and arbitrary intersections, so that you can check by reducing to corresponding statements on ideals. So that needs a little bit of check, but it's not difficult to prove. And once you show that, then you have a topology on A and K, and the subspace topology you get a subspace topology on any subset of A and K. So for example, on any algebraic subset of A and K also, you get a subspace topology. And moreover, in particular, this topology has a feature that its largest open sets, its smallest open sets, I should say, its smallest open sets, so a basis of open sets, are basically complements of largest closed sets. And what are the largest closed sets in A and K? Those are given by the least number of equations. So those are the hypersurfaces, so given by one equation. So therefore, the complements of such hypersurfaces are your smallest open sets you get in this topology. And so those are our notation for that will be VF. So this is the location, the locus, sorry, where F is not zero. I mean, that's a complement of the locus where F is zero. So it's a locus where F is not zero. The thing to keep in mind is that this topology is more of a bookkeeping device. So it's not the topological content here that matters in the following sense that, for example, if K is complex number, this topology, one can compare it with the Euclidean topology because CN has a usual standard Euclidean topology, and this topology on ANC is much, much weaker than the classical Euclidean topology. In fact, for example, it's rarely Hausdorff, and every subset is compact. So that's pretty pathological. And on, for example, if you try A1C, one can easily show that. So this is the polynomial ring in one variable. So the closed sets are given by a polynomial in one variable. So that has finitely many roots. So your finite subsets are your closed sets. And so what you get is co-finite topology because your closed sets are exactly finite subsets, except for the whole space. So so this is a really pathological topology. So it's not really the topological, I mean, this is not what is useful for understanding the geometric picture. It's perhaps more of a bookkeeping device. However, so the guiding principle is always the classical topology. So for example, if your algebraic set is over complex numbers, we would like to know what happens in the classical topology, the Euclidean topology. So one thing, for example, here is that over K equal to C, an affine algebraic set is almost never compact except for finite sets. So finite sets will be your only examples of compact sets. And so for compactifying this, because I mean, in analogy with topology, I mean, there are advantages of working with compact spaces. So if you want to compactify an algebraic set, we shouldn't use a Zariski topology. I mean, over an arbitrary field, we only have a Zariski topology. So what we need to do is we need to, sorry, I think, oops. Right way this was. Sorry, I'll correct it later. Oh no, I think I should do this. Yeah, there you go. Okay. So an algebraic geometry way of compactifying them is to introduce points at infinity. So that brings the next topic, which is projective spaces. So I don't know, am I going fast, or is there any feedback about that, or is it looking too fast? Or?
No comments or questions, sir.
No comments or questions. Okay, that's good. Okay, fine. Okay, so now we come to projective spaces. So these are obtained by adding points at infinity to affine algebraic sets. So in this case, affine space. So set P and K, projective n space, to be equal to an plus 1k minus 0. So this is the algebraic way of doing it. Look at an plus 1k minus the origin and go modulo the scalar action by k star. So that means that you consider two points to be equivalent if they are if there is a lambda in k star which multiplies one to the other, so non-zero scalar which multiplies one to the other, and that's the same as a set of all lines through the origin in an plus 1k. Because if two elements are scalar multiples of each other, they lie on the same line through the origin. And so we'll write the class of a point as a ratio like this, because one should think of them as simultaneous ratios of all the coordinates. So this is the ratio of all the coordinates. So the point B is written. Sorry. Okay. We'll let h infinity be the locus xn plus 1 equal to 0. So this is the vanishing of the last coordinate in in the projective space. And so they will call this as the hyperplane at infinity. This is an ad hoc choice, but I mean, it's sort of convenient initially to think of it that way. And if you do that, then if you assume that the last coordinate is non-zero, then the complement, which is, sorry, if you assume that the last coordinate is zero, then the complement, which is the last coordinate not zero, is in natural bijection with affine n space, set up as follows. So take your n+1 coordinates and simply, because it's simultaneous ratios, you can divide by the last coordinate and make it 1. And then just make it equivalent to the remaining n coordinates. So that is a1 over an+1 all the way up to an over an+1. And so one can think of projective space, therefore, as affine space together with what I called as hyperplane at infinity. And so why is this called as hyperplane at infinity? So for that, one can intuitively think as follows. So take a point in this so-called hyperplane at infinity. So take a1 to an with last coordinate 0. Then what you can do is you can think of this as a limit of a1 to a1, a2, an colon 1 is to 1 over t as t goes to infinity. Which so now since you are in projective space and you are taking simultaneous ratios of all the coordinates, you can simply multiply by them any common scalar. So you multiply them by t, and you get this. And that's what I had done here. I had set up a one-to-one correspondence between the affine space and the locus where h infinity is the complement of h infinity. So so you are now this you can think of these n coordinates as giving you a point in an, and as t varies, you actually trace a line in an, and this line is through a1 to an, passing through the origin. So this is what you get here, and in fact, you can also add a constant here, and it still is the same thing because once you divide by t everywhere, the constant doesn't matter. So this gives you a parallel line to L. And what this tells you is that P is in some sense a sort of a limiting point to points on these parallel lines, set of parallel lines. I forgot to draw a picture, so maybe I can draw it here. Let's just say a bunch of parallel lines, and I am assigning one point at infinity. So that is my point P here. So P is my point here, and L is one such line, and you have a bunch of parallel lines. And for all the parallel lines, I'm assigning one point at infinity. So it is in that sense one can think of H infinity as a set of points at infinity corresponding to various lines in affine space in various directions. So for every direction here, I have a point here, and that's what it is. So P and K is affine space plus one point at infinity for every direction. That's what it is. Okay, so once we have this, one can now set up algebraic. One can now look at algebraically defined objects in projective space, and that way we'll get a larger class of objects. So here's what we have. A projective algebraic set is a common zero locus of a bunch of homogeneous polynomials. So I'll very shortly say why one should look at homogeneous polynomials and not arbitrary polynomials. But let's first say what it is. So it's the common zero locus of a bunch of homogeneous polynomials, simultaneous zeros of that. So which is the same as zeros of the ideal generated by this homogeneous polynomial. And so yeah, in fact, the reason is given below here. Basically, why we look at homogeneous polynomials is the following. If you take a homogeneous polynomial, it'll have the property that if you simultaneously multiply all the coordinates by lambda, the lambda comes out. So f is so the zero locus of f is a union of lines, and that lines to the origin, and that's what we want because we want the zero locus to correspond to something in projective space, which is a bunch of lines. So that's why we insist that we only look at homogeneous polynomials. Homogeneous polynomials will their zero locus will always consist of union of lines through the origin. And so therefore, I look at ideals which are generated by homogeneous polynomials, and such ideals are called homogeneous or graded ideals. So here it is, an ideal I in the polynomial ring will be called graded or homogeneous if it is generated by homogeneous polynomials, and one can easily show that that's equivalent to saying, so this needs a little bit of manipulation, but it's equivalent to saying that if you take the ideal I, then it splits up as direct sum of the degree d parts of I. So ID is the set of all degree d homogeneous polynomials in I. So take the ideal I and take a polynomial f in I and um, yeah, okay, I can say even more. If you give me any polynomial f in I, then in fact all its homogeneous parts of different degrees, if you split it into homogeneous parts of different degrees, then each homogeneous part will also be in I. So I think I could have added that also as a condition here. And all those are equivalent conditions, and that's equivalent to this statement here, that it's a direct sum of the degree d parts of I. So exactly those homogeneous polynomials which lie in I. So these are easy facts in algebra, which you can prove without much difficulty. And so these are called homogeneous or graded ideals. And the largest such homogeneous or graded ideals is the ideal x1 to xn plus 1, and it always contains all the other homogeneous ideals. So our convention will be that we will only look at homogeneous ideals which are strictly smaller than this largest maximal homogeneous ideal, which is often called as the irrelevant ideal. Okay, so this is how we define projective algebraic sets. So these are again given by polynomials, but now we look at homogeneous polynomials, so that we have a zero locus consisting of union of lines, which are nothing but points, a union of lines in affine space, which are nothing but points in projective space. So one can think of projective space as affine space together with points at infinity which have been added. And because of that, it turns out that P and C is in fact compact in the Euclidean topology. So this is the compactification we were seeking. And in fact, the same will also be true about projective algebraic sets, because they are closed subsets in P and C in the Euclidean topology, because they are given by vanishing of some polynomials. So they will be closed subsets of P and C in the Euclidean topology, and so therefore they will also be compact. And PNC is compact because, I mean, essentially, you can show that it is actually the quotient of the sphere in R2n plus 1. Essentially, when you're quotienting out by C star, you can think of C star as R plus, I mean, R star, R plus cross S1. And so you first go modulo the action of R plus, and then you'll get the unit sphere. And so it's a quotient of the unit sphere. So in fact, PNC is compact in the Euclidean topology. And so therefore, that's why this is a useful thing to do. And this is a purely algebraic way of doing it. So you can in fact do it over any field, any algebraically closed field, or any field in fact. So the Zariski topology on P and K, again, we are coming back to this more pathological topology, not the classical topology, not the Euclidean topology. So Zariski topology on P and K is again defined as before. So declare all your closed sets to be exactly the projective algebraic sets, the zero locus of the zero loci of bunch of polynomials. And you immediately see that in particular, what we designated as the hyperplane at infinity is one such example of a closed set. And so the complement, which we said is in bijection with A and K, is in fact an open set. And so we get a decomposition of P and K as an open set, disjoint union, this closed set, affine space, and the hyperplane at infinity. For example, if you do P1K, in particular, you can see that this is A1K, and there's only one point at infinity because any point. So P1K is basically in lines to the origin in A2. So if you go through the definition, you'll see that it's basically points of the form A colon 0, which is nothing but 1 colon 0. Okay, so it's just one point at infinity. So in general, so here the hyperplane at infinity was designated to be the locus where xn is equal to 0. But there's nothing special about the last coordinate. It's just a convenient choice. So if you're willing to be more flexible, then in fact you can pick any I, and then you can say, okay, let's look at ui, which is the locus where xi is not 0. So that will correspond to an, just like before. Simply divide by the ith coordinate instead of the n plus 1 coordinate. And so by doing that, we in fact get an open cover of P and K by affine spaces. So P and K is therefore is an open is a union of n+1 open sets, each of which is looking like the affine space. And if you want to keep track of the coordinate rings, see these affine spaces, they intersect with, I mean, there is a non-trivial intersection between these affine sets. And so you cannot arbitrarily set up coordinates on each one of them independently. So if you want to keep track of the coordinates on each UI, what you should do is the affine coordinate ring of UI should be basically, because we are going to divide by the ith coordinate here, you simply divide by the x ith coordinate here. And so look at x1 over xi to xn+1 over xi I mean, just like you did here. And so that, if you're familiar with, I mean, I'll assume that you know what is called as localization. So basically, you can invert an element in any ring, or you can invert more than one element. So if you invert xi, that is usually denoted as sxi. So this is my ring where xi has been inverted. And this ring, again, you can, it'll have a sort of grading on it. And you can look at the degree 0 fractions there. And those are exactly polynomial expressions in these variables. So it is written as S bracket xi. So this way of writing allows us to keep track of the coordinates on each UI. And when you switch over from one UI open set to another UI, you can use these symbols here. So we are using x1 to xn+1 from the original polynomial ring, which was used to set up P and K. Having done all this, we can now define a projective algebraic set V. We can now define the coordinate ring, the homogeneous coordinate ring. We can now assign a homogeneous coordinate ring to a projective algebraic set. So that is nothing but, again, the polynomial ring modulo the functions, ideal of functions which vanish everywhere on this algebraic set V. So this algebraic set V, it was defined by as a zero locus of I, but so certainly every function in I will vanish on V, but there might be more. So sometimes there are more. So you should actually look at all functions which vanish there and then go modulo that. It turns out that this is also a graded and homogeneous ideal. So it's also generated by homogeneous polynomials. And so therefore, by definition, if you look at S had a nice breakup into various degree D homogeneous parts. It's just a collection of various homogeneous forms. And by construction, IV also has this property. So therefore, S mod IV will also have a property that it breaks up into degree D part for each D. And so it's a ring in which admits this decomposition. So this is the grading on the quotient ring S mod IV. This is my coordinate ring, which I'll call it as KV. So it's what is called as a graded ring. Maybe I should talk about it a bit more in the next lecture. I'll come to that later. So this is a graded ring. And I should warn you, however, that the elements of KV, unlike the affine situation, here they are not functions on V. Instead, what one should look at is ratios of homogeneous polynomials of the same degree, because of this property that we did some time back, that if you multiply each xi by lambda, then it's the same power of lambda that should come out, so that your ratio is defined unambiguously. And so therefore, both G and H should have the same degree. And so we assume that G and H are homogeneous of same degree, and only then the corresponding ratio will make sense on, well, lines in AN+1 through the origin, which is same as points in Pn. So these ratios make sense on points in Pn only if you are, if they are homogeneous and of the same degree. And so that's what we do. And of course, we also must assume that H is not 0, otherwise it doesn't make sense. So these are the only kind of things which make sense as functions. And so elements of KV, unfortunately, do not make sense. Even the polynomial ring S does not consist of functions on projective space. So what are functions on projective space? Algebraically defined functions on projective space. I'll come to that shortly within a few minutes. So what we have is, therefore, that for the affine open cover, so we gave an affine open cover for projective space just now by insisting that the ith coordinate is not 0. So if you look at this affine open cover of P and K, then you can intersect that with any projective algebraic set defined here. So instead of P and K, I'm now looking at a smaller algebraic set V, and I intersect it with this affine cover. Then what I get is a covering of V by Vi. So these are closed in UI, and In fact, I must have said it here that, sorry, I'm scrolling too much here. In fact, this was a homeomorphism. That's kind of not hard to see. It's not just a bijection. It was, in fact, a homeomorphism under the Zariski topology. So this is homeomorphism under the Zariski topology. And so what we have is that, sorry, where was I? I was here, yeah. A VI give you closed sets in UI, which are affine space. So in fact, any algebraic, projective algebraic set in P and K also admits a similar kind of breakup, or it's not a breakup, it's an open cover. So it also admits an open cover like this, namely this V intersection UI by intersection. And this open cover has the property that these are all affine algebraic sets. And so you can associate coordinate rings to them, which are in fact functions on VI. So the coordinate ring to VI will be a bunch of functions on VI. And the way to calculate these this coordinate ring is to put xi not equal to 0. So that is invert xi and look at the degree 0 part. So take the homogeneous coordinate ring of kV, invert xi, the image of xi in V, and look at the degree 0 part. So it's the degree 0 part of this ring. Okay, so so far what we have done is we have talked about affine algebraic sets, affine space, affine algebraic sets, the Zariski topology, projective space, and projective algebraic sets, and the homogeneous coordinate rings on them. So the next thing we'll do is we'll look at quasi-projective algebraic sets. Maybe I can just ask, are there any, I mean, is there any feedback or question? I mean, or maybe everything will be discussed in the end, I think. Okay, so here is the next topic, which is I'll look at quasi-projective algebraic sets. So quasi-projective, so this is slightly more general in the sense a quasi-projective algebraic set or a quasi-affine algebraic set, which is in fact a special case of quasi-projective, as you'll see, is in P and K. So quasi-affine in A and K is an open subset of a projective algebraic set. So we are not just looking at closed subsets of P and K, we are looking at locally closed subsets, meaning open subsets of closed subsets of P and K. So closed subsets will be projective algebraic, open subsets of that will be quasi-projective. And quasi-affine will be open subsets of closed subsets in E and K. Closed subsets in E and K are affine algebraic, and quasi-affine are open subset of that. Since we already said that projective algebraic, we already said that A and K can be thought of as an open subset of P and K. So therefore, one can, in fact, think of quasi-affine as a special case of quasi-projective because A and K was nothing but an open subset of P and K. So in some sense, everything so far is happening inside some P and K for some N. So let's take such a quasi-projective algebraic set, and one can now introduce a notion of functions. So we had difficulty in defining functions on projective spaces. So we will now look at that. So essentially what I want to do is I want to look at those ratios. But those ratios are not defined everywhere. So a regular function on X is a function f x to k such that locally it's given by such a ratio, where G and H are of the same degree. And of course, I forgot to say, but H is not 0. I mean, that's understood when I write a fraction like this, that H is not 0. So you can find neighborhoods, and these neighborhoods are again, so this is one place where Zariski comes in. So Zariski neighborhoods, because these are the open sets which are defined algebraically. Even when K, I mean, of course, when K is not real numbers or complex numbers, then we don't even have a topology. But even when K is complex numbers, we want to look at open sets which have which are constructed algebraically. So that's why we look at only Zariski neighborhoods. So over Zariski neighborhoods, if we are able to write like this everywhere, then we'll call such a function as a regular function. And it turns out one can easily see that you can add and multiply such regular functions. So they form a ring. So that's the ring of regular functions. The local nature of the definition tells us that, in fact, one can glue such functions. So here's the gluing condition. So what it says is that take an open covering of X. X is quasi-projective.
Suresh, there's a question.
Yeah.
What is the small Zariski neighborhood?
Sorry, what was?
What is a small Zariski
No,
name?
small is sorry, is a bad notation. So bad thing. If you want just Zariski neighborhoods around any point. That's what I meant. Is that okay? I meant that around every point in X there is a neighborhood, a Zariski neighborhood U, such that this happens.
Okay.
So that in that sense I meant small. I mean you just have to around every point you have to find a Zariski neighborhood, Zariski open set. So as a small is misleading. So if X is covered, the local nature of this definition here, because it's defined locally like this, immediately tells you that you can glue things. So for example, if X is has an open cover UI, and then what you can do is you can look at these maps here. So what are these maps? These are restriction maps. So any function on X restricts to a function on UI. And any function on UI restricts to a function on a smaller open set, UI intersection UJ. So send F to its corresponding image in the restrictions here. And here send a function G, G alpha, because there are a bunch of functions here. In each coordinate, there's a function here. So send the sequence G alpha to differences. I mean, basically G alpha in G alpha or U alpha beta will either go to G beta or minus G alpha in the alpha coordinate. So when you do that, so these are your restriction maps. When you do that, you will see that any function from here lies inside the so-called equalizer of these two maps, which can be thought of as I mean, the kernel of this map, so to speak. I mean, you can think of it as kernel. That's why I said exact sequence. I mean, if basically these are rings, so one can't really call them exact in that sense, but it's exact, I mean, pretty much in every other sense. So these are the functions which go here. And I meant to draw a gluing picture here. So basically, let's say I have sets here, and I will have maybe, so what it means is that every function here goes to a function here which will have equal images in these. And conversely, if I give you a sequence of functions here which have the property that they go to 0 in this, meaning that their images, yeah, I mean, if I give you, yeah, I mean, here's the map. So in fact, if I give you a sequence here whose image is 0 under this map, then in fact, there's a unique F which comes from here. So it's in fact exact on the left also. And so intuitively, all it means is that if I give you specifying a function on the union of these three open sets is the same as specifying a function here on a first open set, a function here, and a function here, such that on the overlaps, they agree. So that's all it means here. That's what this condition here means. And that's what the exactness, so to speak, here means. Exact is more or less what you would understand. F goes to F restricted to UI, and then the composition should be 0. And what one is saying is that, in fact, it's exact on the left also, so to speak. And this follows immediately from the local nature of the definition. So this is not hard to show. And therefore, one can actually use this to calculate things, provided one has a basic technical fact. So before that, let me point out that if you have an affine algebraic set, we already had one coordinate, a candidate, we already had a ring associated to it. It was a 0 locus of some ideal, and simply look at polynomial ring modulo ideal. So that was a ring of functions on X. And now I have constructed by a more abstract process, or no, I won't say abstract, by a general process, I have constructed a ring of regular functions. These are functions obtained by which are, so for quasi-projective, or instead of quasi-projective, if I wrote affine here, you would again write G over H, where you can drop the homogeneous condition if it is not in AN. If it is not in Pn, if it's in AN, then you can just drop the homogeneous condition and just say it's given by a rational function like this. So basically, these are functions which are supposed to locally look like rational functions. And these are globally polynomial functions. So I have two such rings, and I have a natural map between them. And the basic technical fact, which I'm not going to prove, is that this map is an isomorphism. So this thing keeps coming up again and again, that for affine algebraic sets, nothing new happens. And no matter how local you try to define something, you recover what was defined globally. And so in this case, the coordinate ring was defined globally, and you recover that even if you try to go local and look at things which are locally given by fractions, you still get back the globally defined coordinate ring. So this is a basic technical fact. It's just playing around with localizations. And so this technical fact for if A is an integral domain, one can prove this a little more easily by simply saying that this local fractions can be thought of as intersections of these are localizations at the maximal ideal AM, where the intersection is happening in the fraction field. If A is a domain, then these intersections can be carried out in the fraction field, and you can just intersect them. If A is not a domain, basically you don't know how to define these intersections, and that's the technical problem, and that can be overcome. But I will not get into it. You can, I mean, I can give references for this if for those who have not seen it and who are interested, so you can look it up. So this basic technical fact tells you that for affine algebraic sets, this ring of regular functions is not a new thing. It's just your coordinate ring. But for quasi-projective ones, we still don't know what it looks like, but we have a recipe here. And this recipe tells us that one just has to glue things over an affine cover and then see what you get. And that will give you your regular functions. So if you carry it out, then, for example, you can prove that for projective algebraics, for projective spaces, there are really no globally regular functions except for constants. And this might be familiar to you from complex analysis. For example, when n equal to 1, P1C is the Riemann sphere. Sorry, it's the Riemann sphere, the extended Riemann plane. And we know that by Liouville's theorem, regular function, the holomorphic functions on the Riemann sphere are constants. So that is reflected algebraically here. So for projective space, it's K. And so what this tells us is that the ring of global regular functions on projective space gives us no information about what this space looks like. Unlike affine space, where we don't have to worry about, first of all, this regular functions is the same as coordinate functions, and this carries all the information about the affine space. I mean, you can recover all of X using the coordinate ring, whereas for projective space, you cannot. I mean, basically, you get very little. So therefore, one has to go local again. And so that's what we'll go. And I will come to the last topic for my lecture today. So these are some generalities. So for any quasi-projective X, what I do is I try to go local, which means for every Zariski open U, I assign this ring OU. This is the ring of regular functions. And so this assignment forms what is called as a pre-sheaf structure, which is just a fancy name for saying that I have a functorial assignment from U to OU, where functoriality means that if I have V inside U open sets, so this side, the category is just the category of all open sets in X, maps being just restriction maps. And then I have a homomorphism from OU to OV. Basically, any regular function on U restricts to a regular function on V. So I have this restriction homomorphism. So this assignment is functorial, and that is, in fancy language, it's called a pre-sheaf. And since I'm assigning a ring to each open set, it's called a pre-sheaf of rings. So this is what we deal with quite often. We look at pre-sheaves of rings, and there is an additional property we have here for OX, which is that it satisfies the gluing condition, which was mentioned above, that if I give you, so this is the gluing condition here. So if I give you an open cover, and if I give you intersections, then any function here, any collection of functions on each of these open covers, so any sequence here, which agree on the overlaps, which means it lies in the kernel of this map, actually comes from a unique globally defined function. So this is called the sheaf property, and OX, this assignment U goes to OU has this additional property that it's in the very local nature of the definition of regular functions that a global regular function on X is simply the same as giving one locally which glue together, which agree on overlaps. So that is called the sheaf property, and I'm not technically defining it, but I have more or less said what a sheaf property is. So a pre-sheaf which has this additional gluing condition is called a sheaf of rings on OX, on X. So OX is a sheaf of rings on X. So a function x to y between quasi-projective algebraic sets. So we had difficulty even defining functions x to k. So for projective algebraic sets, only for affine we knew how to define it. But finally, we could use global this regular functions to define it actually. So one can now use this gadget to also define maps between quasi-projective algebraic sets. So for unlike affine situations where in the beginning of the lecture I said that you simply look at maps of coordinate rings in the reverse direction. Here it's a little more complicated. So a function between quasi-projective algebraic sets is called regular if it's continuous, and for any open set V in Y, when you pull it back, I mean, when you compose it with phi, you get a regular function on f in phi inverse v. So you take an open set here and take a regular function there, pull it back via phi, you should get a regular function here. So it pulls back regular functions to regular functions. If that happens, we will call it regular. And biregular maps will be called isomorphisms. And again, we see this phenomenon that here's a basic technical fact, which I'm not going to prove. It's not hard to prove, but it's somewhat technical, so one has to just chase through things. Is that for affine algebraic sets, nothing has changed. A regular map in this more general sense between affine algebraic sets is same as what we knew before, just polynomial map. It's only for projective spaces and quasi-projective algebraic sets is where we have to use this kind of more general definition, because there's no really way of globally capturing things, because globally we have very few functions at hand. So we really cannot use global functions to capture this kind of definitions. And finally, a few more things. An arbitrary algebraic set is obtained by gluing affine algebraic ones. So so an arbitrary or abstract algebraic set. Now it's no longer sitting in affine space or projective space. It's not quasi-projective or anything. So one can, just like one defines manifolds by as topological space, which is locally defined, locally given by Euclidean balls, or complex manifolds, which are locally given by open subsets of complex Cn. Similarly, one can define algebrogeometric objects more abstractly by gluing local ones, and local ones are essentially the affine algebraic ones. So an abstract algebraic set is a topological space with a sheaf of rings, OX. So again, let me remind you, sheaf of rings just means that for every open set here, I have to give you a ring. And it's punctorially defined. So whenever I have restrictions, I have restriction maps of rings, so ring homomorphisms. And there's a gluing condition. So if I give you an open cover, and if I give you a function from each of these elements of the open cover which agree on the overlaps, I should get a unique global function which agrees with that, global element of the ring which agrees with that. So that is called a sheaf of rings, same definition as above. So is a topological space with a sheaf of rings such that there's an open cover of X, say UI, such that there are isomorphisms. So these, over this open cover, my abstract algebraic set should look like affine algebraic set. So here some technicality is hidden. Basically, isomorphism means that see, this side is a topological space with a sheaf of rings here. So the small thing I should write here, I should write it as OX restricted to UI. Okay, so OX restricted to UI. So this is a topological space with a sheaf of rings here. And when we say isomorphism, I mean that it should be homeomorphic to an affine algebraic set. And moreover, under homeomorphisms, I know that, so I have open sets corresponding there. And so I should be able to transport my sheaf of rings here to a sheaf of rings here. And that should agree with my sheaf of rings that I already have on the affine algebraic set. So that is what isomorphism means here. And so therefore, an abstract algebraic set is one which has a sheaf of rings which locally looks like affine algebraic sets. So it's basically locally, it is looking like affine algebraic sets, and I glue them together and I get a global one. That is what, in fact, you should think of projective space as, but projective space has additional structure. It has this homogeneous coordinate ring. And we'll exploit this graded structure later on. We'll use that later on. But one can, in fact, define abstract algebraic sets like this. So I think my time is almost running out. So I'll take a few minutes. Is that okay, Anand? Just a couple of,
yeah, just a couple of minutes. Okay.
Yeah. Okay. So just the last thing. So let X OX be an algebraic set, abstract algebraic set as defined as above. Now on such an abstract algebraic set, we have already a sheaf of rings, which we just said here. I mean, it has a sheaf of rings, which is locally looking like an affine algebraic set. So it has a sheaf of rings. It's not enough to look at the sheaf of rings. I mean, in algebraic geometry, what is convenient is to also look at the category of modules. And so here a sheaf of OX modules means a sheaf of abelian groups, which means, again, what does sheaf of abelian groups means? It again means the same thing. You functorially assign to every open set an abelian group. Functorially means under restrictions, you should get homomorphism of abelian groups. So group homomorphisms. And again, the gluing condition should be true. So over an open cover, if you have a bunch of elements from various groups over various open sets, which agree on overlaps, I should have one defined globally, a unique one. So, so if I have a sheaf of abelian groups, then I should, so we will call it, OX module if there is a scalar action from O. That means for every open set, so here I forgot to say V is an open set. For every open set, I have a scalar action like this, which is compatible, which has some obvious compatibility condition. It is compatible with restrictions because all of these you can restrict to smaller open sets. And so you will have restriction maps, and so it should be compatible. Okay, so I'll end with two examples. So this is what I was supposed to talk about today, but I thought I'll first create the background and then I'll get into these things. So first example is X is an affine algebraic set, let's say with coordinate ring A. So in this case, if you remember, coordinate ring is just simply the restriction of polynomials to your affine algebraic set. And that's the same as regular functions, no difference. Take a module M. Then you can give a basis for the Zariski topology on X, and the basis for Zariski topology on X is the hypersurface complements. So these are your smallest open sets because their complements are the largest closed sets given by vanishing of one equation instead of many equations. So I take this basis, and on this basis, I assign XF goes to MF. And if I do that, then it turns out one can easily show that it extends to a unique sheaf on X, and which is in fact an OX module. And this is denoted as M tilde. So these are my basic examples of, these are what are called as quasi-coherent modules on sheaf of quasi-coherent OX modules. I'll talk about them more next time. And similarly, one can, okay, I think it's ending here. So similarly, one can say something about projective spaces. If X is projective space, then one looks at the graded coordinate ring instead of the usual coordinate ring. But now the graded coordinate ring, if you remember, is not consisting of functions on X. There are very few functions on X actually. But nevertheless, it's a useful device for keeping track of various coordinate rings. So of various open sets. So if A is equal to Kx, now instead of looking at all modules over A, it's more useful to look at graded modules. And so let M be a graded module, which by definition, so I'll probably specify it again, simply means that M again splits up as direct sum of various degree D parts. So M is a direct sum of, so this is actually a direct sum of various MDs for D greater than or equal to 0. And so then this XF goes to MF. So XF is my basic open set where F is not 0. So again, F is a homogeneous polynomial on the coordinate ring. It's not a function, but the locus where F is 0, one can show is well defined. So therefore, one still gets, or you can just think of F equal to 0 as a hypersurface in Pn. And intersected with X, that gives you a closed set. Look at its complement. So this is your XF. So XF is the complement where F is not 0. And corresponding to that, one can give, one gets graded ring, and the corresponding graded ring is AF, which is the degree 0 part of AF. So this is degree 0 part of AF. And if you do this assignment, so on, so this is, so here what you have here is an open subset of X. And for this open set, if you assign this, then since these open sets will form a basis of open neighborhoods on X, again, one extends, this extends to sheaf. So extends to a sheaf. Sorry, I need to write it better, but okay, I'll just write it now and end the lecture on X. So this, and it is called as M tilde. So again, it's an OX module. It is called as M tilde. So these are pretty much our basic examples of modules that we will be studying over affine or projective spaces. More generally, if you have something which is neither affine or not projective, we will cover them by affine things, and we will then say that something is of this type if it over affine pieces it looks like this. And in fact, this projective definition is a special case of that. On affine pieces, it will actually look like MF. It will look like this, MF. So in fact, M tilde F, if you like. So I'll talk about these points in the next lecture. Okay, so I think I've reached the end of my lecture. Thank you.
Thanks, Suresh. Are there any quick questions? Suresh, you are able to see the chat?
Let me go to the chat. Just a minute. Something showed up on my screen. Yeah. Okay. Let's go to the chat. Yeah. Okay. Okay. So let me start from where. Streaming. Fine. What is infinity for a generic field? No, infinity is just an abstract point for a generic field. There is no such thing as infinity as such. So this is an algebraic way of introducing a point at infinity. So for a real line, so I'm addressing Shrikant Pai's question. For a real line, one can think of one is assigning a 1 point at infinity. Note that you're not assigning 2 points at infinity. You're only assigning algebraically 1 point at infinity. And for the complex plane also, you're only assigning 1 point at infinity. So in general, for P1K, one is introducing 1 point at infinity. It's just an abstract way of introducing it. There is no further meaning to it. So, okay, I don't know where you are referring to infinity. If you are referring to it as limit t goes to infinity, where I said that is just an intuitive argument, which you can think over happening over real numbers. Or an arbitrary field, of course, that makes no sense. Okay, then Vignesh, is there no concept of norm or order? You may, if there is no, okay, he's talking about 1 point compactification. Yeah, but I won't call it as 1 point compactification because for A1, I'm introducing 1 point, but for A2, I'm introducing several points. So it's not a 1 point compactification of Rn in any way. For An, I'm introducing infinitely many points in every direction, or every for every line through the origin. So every direction meaning in both ways, both directions for that line. But for every direction, I'm assigning 1 point at infinity. So there are infinitely many points at infinity for A2 onwards. So small Zariski neighborhood has been clarified. Direct sum as abelian groups. Where is this direct sum?
So this was for the graded module. When you wrote down graded.
Yeah, direct sum as abelian groups. Yes. Can you please explain the reasons behind the terminology quasi-coherent? Yeah, one might as well call it coherent. So it just means that they are sort of compatible in a nice way. So you can call them coherent, but the only reason for quasi-coherent is that the word coherent is reserved for finitely generated modules. But otherwise, I mean, if you want to, you can think of it as coherent. I mean, there's nothing quasi about it. It's just that it may not be finite. So for finitely generated modules, we have a separate terminology. And so that is called coherent. And for non-finitely generated modules, it's quasi-coherent. But if you ask me, I mean, they all look coherent to me.
Okay.
Yeah.
Maybe now is a good time to open up the floor for discussions.
Okay.
Yeah.
So what should I do? I'll okay.
I think both you and Shamik should just hang around and answer questions.
Yeah. So I don't have to eliminate any screen or anything, right? You will just
no. I think if anybody asks a question, you need to show something. Then maybe you can show.
Okay. Sure. Okay.
So I think just to make this more streamlined, what we can do is people can just post in the chat their question, and then the relevant person can maybe answer it.
Okay.
That may be the easiest way to go about it. We can tweak it, as we go along if necessary. So the floor is open for discussion with both Shamik as well as Suresh. Alternatively, you can raise hand. You can use the raise hand feature, and I'll ask you to unmute yourself and speak. Okay, this is a question for Shamik in the chat.
Okay, so what is the question? Do the pair co-fibrations mean an orthogonal set of morphisms? Yeah, I don't quite understand what is an orthogonal set of morphisms. So,
I think
I don't know what is the definition of orthogonal set of morphisms.
Okay, let me try. It's like AP and mono. So suppose if you have, how do I say it? Suppose UF.
Shamik, in the meantime, maybe you can answer this question. Two spaces X and Y have same homotopy groups. Does it mean that the spaces are homotopy equivalent?
No. I mean, abstractly, there should be a map between them, which induces the isomorphism. Just having abstractly the same homotopy groups does not guarantee that they are homotopy equivalent.
Okay. Yes.
Okay, now
Yeah, show me something like this. F is a co-fibration.
Yeah.
And M is a vibration, and you have this diagram.
Yeah.
Then there exists a unique W which makes this.
No, it will not be unique. You see, in
this will not be.
No, it will not be unique.
No, unique up to weak equivalence.
Yeah, it will be unique. Any two such extensions will be homotopic. Any two such lifts of homotopies would be homotopic. That's the thing. You are. This is like the lifting property for cofibration and versus fibration. So, two lifts will be homotopic.
Okay, that means you are saying in this place it will be unique. In the homotopy category, it will be unique.
Yeah. In the homotopy category, it will be unique.
So it makes a prefactorization system.
Prefactorization
in the homotopy category
system. Yeah, actually, I'm not familiar with this terminology, prefactorization system, but yeah.
Okay. All right.
There is a chat by Vignesh Subramaniam. It says yes, it does.
Okay. So,
any other questions, comments? Suresh, there's a question for you.
How do we see projective space is basically cover projective space by two open sets. A1, basically, for example, look at, let's say P and C, for example. Suppose the field is complex numbers. Then you can cover it by two Zariski open sets. One is the finite plane, that is A1C, which is the usual complex plane. And the other is is a similar neighborhood around infinity. So you remove the 0 point and instead you add the infinity point. So it's as if you're taking 1 by z. So if z is your variable, a complex variable for one of the copies of A1C, then 1 by z is your variable for the other copy of A1C. And so the two coordinate rings that you get of these two affine open sets are CZ and C1 by Z. And you take their intersection, and that will be C. So same argument will work for any field K. So this is for P1, and for Pn, in general, you will have to again cover it by n+1 open sets. And what you will get is, similarly, you will get polynomial rings of the form K. For example, if you take P2, then you'll get kxyz with, suppose you invert z. So you'll get kx by z, y by z on one affine open set, and then you'll get k x by y, z by y on another affine open, and similarly k z by x, y by x in another open. And you have to take the intersection of these three rings. So that will again turn out to be just scalars. So it's like that. You have to just do a calculation like this for n+1 affine open covers for P and K, simply by putting ith coordinate not equal to 0 and inverting that variable and looking at x x1 to xn+1 over xi. I mean, when you take the ith coordinate not equal to 0. So that is the coordinate ring you will get in the ith open set, and means x1 over xi, x2 over xi, up to xn over xn+1 over xi. Polynomial ring in that is what you will get as the affine coordinate ring for ui. And now take the intersection of all these, because you're looking at elements in each one of these which agree on overlaps, which basically means you're intersecting them. So you take the intersection of these rings, and what you can see is that that is k, because there's nothing which has a denominator in, I mean, there's nothing which has everything will have, I mean, there's nothing which has denominator in all the xi's. And sorry, what am I saying? Which is neither a denominator, whatever. I mean, if you intersect the rings, you'll see that. Yeah. Okay, good. For n equal to 1, you got it. Okay, so then just try it for irons.
Any other questions?
Akashdeep Viswas, in the definition of quasi-coherent sheaves, did we have X to be quasi-projective or just projective algebraic set? I mean, for quasi, no. Yeah. So X could have been quasi-projective. In fact, X can be, I don't remember where I put the definition. X can be any algebraic variety, any algebraic set. So abstract also. That quasi has nothing to do with the quasi that I was, that comes for modules. And does it extend uniquely? Yes. So what is the general result is that if you have a basis for the topology, and on that basis I specify an abelian group, or I mean something, a module, such that the compatibility condition holds for those restrictions of those basis, for intersections of those basis neighborhoods, then in fact it will uniquely extend to a sheaf. So that's the general result. Again, it's a very generic kind of result. So it will, I mean, as long as, so in this case, I have a basis of neighborhood. So I will get a, it will extend uniquely. As far as definition of quasi-coherent sheaf, yeah, that's what it is. So for a definition of quasi-coherent, I'll define quasi-coherent sheaf next time. So yeah, it doesn't have to be, it is a very general thing. It's defined on any abstract algebraic set, or in fact for any scheme. We'll talk about it next time. Shrikant is asking, Shrikant Pai is asking, is there an intuition for the term coherent? I suspect it only means that the that means that they are sort of compatible. I mean that's how I think of them. So there is no funny thing going on. Basically, you can't simply I mean it's yeah, I don't know. I mean I don't know if there's anything more than that. I don't think there's anything more than that.
Hi Suresh, this is Shrikant.
Yeah.
Just to clarify, when you answer Shubhrajit's question, can you please explain the reason behind terminology quasi-coherent? You said you could think of it as coherent and really quasi is not required. It's almost coherent.
No. I didn't mean, so I should be careful. That's what Pranav was also complaining to me. So The definitions of quasi-coherent and coherent, which I have not defined today, are similar. Just that for coherent were similar, at least for for what are called as Noetherian, or in this case for abstract varieties or quasi-projective varieties or whatever. They are similar. Their only difference is that in one case I insist that the modules be finitely generated, then I call them coherent. And in one case I insist that the modules be they can be any arbitrary module. So in that case it's quasi-coherent. So coherent is quasi-coherent plus finitely generated, at least for algebraic varieties or what are called as Noetherian schemes. Coherent is nothing but quasi-coherent plus the extra condition of being finitely generated. So to make a distinction between them, one of them is called coherent, one of them is called quasi-coherent. So that's the only, I mean, at least at the initial level, this is how you should think of it. Then because one of them is given by finitely generated, there will be more subtle implications of that. And one of them is given by, I mean, you don't insist on finite generation. So then, I mean, you can have more subtle implications of that. That will come up later.
Other questions? Yeah, I mean, if there are no questions for about a minute or so, maybe we can just end the session. So just wait a little bit. Okay, I think it's time to close the session for today.
Okay.
Okay.
Thanks, Suresh.
Yeah.
Thanks.
Bye.
Thank you.